Any questions? Okay. So today we're going to continue from where we left off. Basically, we would like to cover a couple more interesting formulations and ideas, and then formalize what exactly we mean by formulations, how we can possibly compare them. We'll see if we get there. Okay, so we left off essentially at the max-min idea. This is the idea behind linearization of potentially nonlinear constraints or objectives into a form of linear programming problem. If you can linearize them, then you can probably linearize them in a formulation that involves discrete variables, and therefore you could attain a decent IP formulation. We have taken a look at the following maximization minimization problem, where we have 6 functions, 6 profits. Let's say that each of these profits depend on some variable x, and we maximize over x, and then we minimize among these 6 profits. Basically, you can view it as modeling of the process where you have 6 possible outcomes that you have no control over. Any of them can happen. You have the decision variable x that can affect each of these outcomes, and you would like to be on the safe side. You would like to maximize the amount you will get, no matter which outcome you will end up getting. Essentially, you assume that there is some adversary here that picks the worst outcome out of all 6 of them and gives it to you, and you would like to maximize that. And this formulation can be written as follows. Let's say that z is the variable that basically bounds from below each of these outcomes, each of these profit functions. You would like to maximize over x and z the lowest of these outcomes, at least the lower bound of these outcomes, such that like where this 6 constraints for each either is 1 constraint, this 6 constraints enforce that z actually is the lower bound for all of these functions. By the way, I would like to ask you guys if anyone could turn on their cameras so that I'm not alone on this call. Just for the sake of convenience. It most probably it's the last time we meet on Zoom or on virtually, so it's most probably the last time I'm asking you to do this. Thank you very much. I appreciate it. Yeah. So let us formalize this idea into a form of a formal statement or a regular argument. There's a theorem that says that if you have a function g of 2 arguments, one of them is scalar in R, another one is is a vector in Rn. So you have two variables y and x, where y is a scalar and x is a vector. You have a function g of these 2 variables, and if for each x the function g increases with y, so basically you have g that consists of threads. For each x there is a thread, and all of these threads are strictly increasing with y. Then the problem of maximization over x, over the vector variable of the function g, where instead of the first variable we substitute a minimization over any, essentially here it is a finite set, but it could be like basically, yeah, basically you substitute a minimization over a finite set, and you allow g to depend on x. This problem of maximization is equivalent to the following maximization over x and a scalar variable z of g z x, where you enforce z to be lower bound on all of the functions fi's. basically for all x. We will come back to the proof of this statement. In this statement directly, you are dealing with maximization of minimization. Therefore, this is the maximean case. Similarly, you can formulate a similar statement for min-max objective, where you have minimization of a function that depends on the maximum. Similarly, you just need g to be increasing with y, and that will lead us to the equivalence between these two programming problems. Note also that the maximum of a function is the same thing as the negative of the minimum of the negative of the function. So you could potentially, these are the only two cases that you can potentially consider, and both of them can their equivalence follows from this statement essentially. Let us put together an example of application. Where exactly could we possibly apply this kind of statement? Suppose that you have a problem where you're interested in the absolute value of a linear function, such that x1 minus 3x2 is greater than or equal than 2, and x1 is greater than or equal than 0. You're minimizing over two variables, like a vector that consists of two entries. How can they possibly convert this into a linear programming problem? Does everyone understand the problem formulation here? Is there any question about that? Is it clear that this objective function is not linear? Why, what are we doing here at all? We would like to reformulate this objective function as a linear function. Okay, so I assume that everyone understands that this absolute value is not a linear function. So how can we possibly convert it to a linear program? First, we need to use the definition or the main property of absolute value, that the absolute value of x is the maximum between the x and the negative x. Therefore, our problem becomes a minimization of maximization between two values. If we just substitute this property into this program. Here you can see that there is a minimization of maximization, but it's not clear still how to use this general theorem for our purposes. Let's consider the following function g of yx is equal to y. So this obviously does not depend on x, and therefore for any x, this function is going to be increasing. So we don't even need to show that g is actually a function of the form that appears in our theorem. Let's try to apply the theorem to this particular case. So I remind you that g of y and x is equal to y, and we can create a new variable z, just as in our theorem, a new variable z. When we write down a minimization objective where we minimize z, such that z is upper bounding. Now it's an upper bound for the two functions between which we were trying to maximize, and the two other constraints remain the same. Now this function here, this problem here, is obviously a linear programming problem. Both of the constraints that we have added are linear because our functions fi's were linear, and the objective is obviously linear because it depends linearly on z, and both of the previous constraints were linear in the original problem. Therefore, our new programming problem is a linear programming problem, and it is equivalent to the one that we have seen before. due to the theorem that we have that we introduced. Now, I have a question before we get to actually proving one of the statements. So this is what we are doing if we are having minimization or maximization, or if we are having maximization of minimization. What exactly can we do if we were to have something like maximization of a maximum between two functions, f1 and f2? Do we need something like this, a statement like this, to reformulate it as a linear programming problem? Anyone?
Maybe just an idea, but I'm thinking maybe we don't, because the program will naturally find the maximum for within the inner maximum. So, or rather, it'll kind of ignore the inner maximum because the outer maximum is already telling it to find the largest possible value. So we may not need to reformulate.
Exactly. Yeah, that's right. That's actually the very correct thing. So maximization. It is important to know that maximization of maximization is just maximization. So you just would need to write down, like, let's say that, yeah, basically you wouldn't probably need to say that f1 is equal to z1 and f2 is equal to z2, and you basically you would just need to maximize z1, z2. So these are the, like, and essentially this by itself would be already a linear objective. So what can we say about the proof of this linearization for max min or min max? Well, first of all, what do we mean by saying that the two problems are in fact equivalent? First of all, it is obvious that if they are equivalent, they should have the same optimal objective value, right? So the solution to this problem, the value of the solution to this problem must be equal to the value of the solution of this problem here. What else? We can also see that the domain, like at least one part of the domain for x, for the first problem and for the second problem, are in fact the same. So we don't need to we can essentially we can say that the problems are equivalent if the axes in the first problem and in the second problem exactly coincide, or there is an option that they can coincide. Okay, so let's start with the value. Suppose that our proof is going to be by contradiction. So suppose for contradiction, the solutions are different, meaning that values of the solutions are different. There are two options that could have happened. Now let's note the z1, z2 star and x2 star. The solution for the second problem, where we have introduced z, and let's introduce x1 star as the solution for the first problem, where we have not introduced z variable. Suppose that the optimal value for the second problem is smaller than the optimal value for the first problem here. Like you can immediately see that this scenario is not possible, just because the point z x, such that z is just the minimum of this functions and x is just equal to x1 star, is a feasible point. Since it's a feasible point, we could just have substituted this point into the function g of z and x, and we would have got a better, like a larger value than the value of g of z2 star x2 star. Therefore, it is not a possible scenario. We came to a contradiction. Now let's assume that our second problem is has a bigger value, a better optimal solution than the first problem. By optimality of the x1 star, the inequality the following inequality holds: the value of the function g from the first, basically the objective from the first problem at the point x2 star must be at least as, at most as good as the solution, the value of the objective function of the first problem at x1 star, just because x1 star is the optimal point for the first problem. By definition of the second problem, z2 star is such a value that is at most as large as the minimum between all of the functions f1 through fn at x2 star, right? Just because we had all of these inequalities at z. From a monotonicity of g of y and x with respect to y, we have that the value of the function g at the point z2 star x2 star must be at most as big as the value of g of f1, g of minimum of the functions and at x2 star and x2 star. This is because this z2 must be smaller than this value here, and our g is monotone. Therefore, we have arrived to a contradiction here. So both of these scenarios are not possible. Therefore, we must have something like g of z2 star x2 star must be equal to g of z of minimum of f1 of x1 star and so on, fm of x1 star comma x1 star. This is regarding the optimal value, and obviously if we have got a solution of this form for the second objective, then the same x2 star can be plugged in to instead of x1 star in order to obtain the same objective value, and the same holds the other way around. So therefore, we indeed have two equivalent formulations for this Maximi intrigue. Any questions regarding the trick and the theorem and how it can be applied? Okay. So basically, you would especially need this example, because you have an example like this in your homework where you are dealing with the absolute value, and this is basically how you can deal with any of the problems of this form. Okay, so let's switch gears to formulations, to providing formulations for problems in textual form. One of the very interesting and important examples of problems in IP is the knapsack problem, or the integer knapsack problem specifically. Let's say that you're trying to break into a vault containing n types of pieces of jewelry. A piece of the jth type of jewelry weighs AJ, and it's worth CJ. You can carry a total of B pounds. How can we maximize the amount of potential value of the jewelry we have got by picking only like the most valuable jewel. First of all, the variables. We are saying that xj is equal to 1 if item j is being selected, and 0 otherwise. We can also extend, so this formulation here, suppose that you have only one type, only one piece of each type in the vault. However, you can also impose that xj is just the number of pieces of jewelry that you're trying to carry out of the vault. The constraints are naturally the weight limit that says that the total weight of all of the items that you have picked up must be less than or equal than b pounds, otherwise you won't be able to carry them out. And the integrality of the variables, xj's must be a positive integer, non-negative integer. The objective function needs to be the total profit, or in other words, so sum across all of the types of the jewelry. Okay, so basically it's this thing. We don't need the other summation. So it's sum of all of the types of the jewelry, the number of pieces of each type that we are getting times its price. It is a linear objective. There are linear constraints, and also there's an integrality constraint here that gives us a reason to think that this is the integer linear programming problem. You can rewrite the formulation. The complete formulation looks like this. You're trying to maximize the objective function, the linear objective function, subject to a single linear constraint. It is very important then that the constraint is like there's only one constraint in this problem. This is what tells us, like this is what differs this problem from everything else. Are there any questions regarding the knapsack problem, the formulation?
Yeah, I had a question. Why is xj, maybe I'm misremembering what z is, but isn't xj binary?
It is, yeah. So there are two ways to think about it. First is you are assuming that in the vault there is only one single piece of every type of the jewelry. There are like in my kind of in the alternative formulation, you can say that xj is there are actually multiple pieces, and there is an infinite number of pieces of each type of jewelry. Therefore, you would need to decide how many items of each type you're going to be carrying out. Therefore, xj is going to be the number of pieces of type j, and then you would need it to be integer and non-negative integer.
In that case, then would we also need to upper bound xj by the total number of pieces of that type?
Yeah, so we could like in this particular formulation, you can say that there is an infinite number of pieces of that type. So there's nothing to worry about. You would never be able to carry everything.
Okay, that makes sense. Thank you.
Any other questions here? This is a good point, because if we were to say that xj that we have only one piece of each type, then xj would be a binary problem, and so xj would be a binary variable, and that would make it a binary problem. Okay. So let's introduce the set covering problem. You're a radical internet anarchist, and you're trying to establish a P2P mesh network so you don't have to rely on centralized ISP. In particular, you have N locations, roof, telephone poles, etc., where you can you can install a piece of like a device, like your network device. You have identified different regions in your area that you want to ensure that your device is covered. For each location, you know the cost of setting up the device as well as which regions it will cover. Your goal is to set up the devices in such a way that all M regions have internet access while minimizing the total cost. So how can we, first of all, can we draw this problem? We have a set of regions. The set of regions R that contains how many M different regions. So from 1 to M. Each circle is going to be a region, and each device is going to or how to say locations. It's going to be locations. So the locations are going to be denoted with squares. You have N of them. You have location 1 and so forth, location N. And each location covers several regions. We can connect them and say that if the square is located with a circle, then a location covers a region. For each of the locations, we have a cost to set up. I think it's C1 through Cn, and you need to cover. So the problem is to choose the device locations, the device placing locations, such that for each region that you can possibly consider, there is a location that is connected to it through an edge. The structure like this is called a bipartite graph because it consists of 2 parts. And it will be a very important graph theoretical structure in the future. For now, it's just a part of the formulation, just for you to keep that in mind. Okay, so let us try to formulate the set covering problem. The set of regions is going to be denoted with M, and the set of devices is going to be denoted with N. This is the same things that are R here and L. So this is not R, this is M, and this is not L, this is N. SI is the set of regions covered if you set up a device at location I. So this is basically, this is the set of circles to which, if this is the location I, then this is SI is the set of circles to which there are edges that go from the square I. CI is the cost for setting up a device at location I. So there is a CI associated with it. And the combinatorial problem is formulation is the following: you need to minimize over the set of subsets of the set N the following linear function, subject to a constraint that the union of all SIs over I's that belongs to T must be equal to M. How can we form? So this is who remembers how this formulation? Okay, it's actually written right here. So this is the combinatorial optimization problem formulation, because we have a linear objective function, and we have the problem set up in terms of sets. We are optimizing over the set of subsets. And we have discussed how we can convert this into a binary linear programming problem. We need to introduce a variable xi that would would tell us if a location I is included in T in the set of chosen locations or not. So 1 if it is and 0 if it's not. The constraints are linear, meaning that so basically we are saying that there's some matrix A that we need to discuss, that after multiplication by a vector x gives us a vector that is greater than or equal than 1. How to construct this matrix A? Well, first of all, we need to understand what exactly this inequality needs to say. So this inequality, each of the inequality in this system needs to say that the number of locations, the number of locations that cover a region, let's say J, is greater than or equal than 1. Basically, we need the left-hand side to express the number of locations covering the region J. How can we do it? Well, if we have our vector x saying in which locations we have placed our devices, then we can construct another vector aj that will tell us which from which locations the region J is actually reachable. So it's going to have 1 on location AJI if the region J is reachable from the location I, and 0 if it's not. So this is what's written here. And if you introduce this kind of vector aj, then after multiplication by x, you would get a 0 if there are no this zeros and ones in one vector and in another vector are misaligned, and you will get at least 1 if there is at least one case where you have 1 here and one in one vector and 1 in the other vector. So this and if you stack vectors aj together, you would get the matrix A. So this is a system of linear inequalities, and the only thing you need to enforce now is that xj is actually a binary variable. What about the objective function? Well, it is just the minimization of the sum over all i's ci times xi, just the total cost of placement of devices in different locations. We ended up with a binary linear programming formulation of this form, where we have a minimization of objective over a system of linear inequalities and binary constraints. Any questions regarding the set covering problem formulation?
I had a quick clarification for this constraint. Is that a vector of ones?
This is a vector of ones, yes.
Okay, so it's the incidence matrix multiplied by a vector of decision variables, and all of those should be greater than, and then it should all be greater than or equal to 1.
Exactly, yes. So the matrix A is called the incidence matrix. That's right. For the graph that I described before. That's right. Any other questions here? Okay. So one very important use of IP and mixed integer linear programming problems is logical conditions, logical constraints. More about this we have covered during the discussion section, but I would like to cover at least one example here as well. It's modeling of just disjunction expressions. When you have, like, suppose we are planning to go shopping, and we have B$1 in cash and B$2 on a debit card. There are two stores in our town. One accepts only cash, and the other only accepts credit cards, debit cards. We have only enough time to visit one of the stores. How can we model the budgetary restrictions of this type? Well, obviously, if we denote Y1 and Y2, the total amount of like the vectors of quantities of goods that we are going to be purchasing in one store and in the other store, and we'll let A1 and A2 be the vectors of prices in both stores. Then our set, our feasible set, takes this form, where basically we have a budgetary constraint for the case when we are going to the first store, and there's a budgetary constraint when we are going to the second store. And since we have not decided yet to which store we are going, we have a union of them. So this is called the disjunction condition, when we have a union of two. A modeling of this is quite straightforward, especially if you put it this way. You just need a new variable that will determine whether you go to the first store or to the second store. Let big M be a very large number that is greater than everything that could ever have appeared in this problem. And we can put together the following set of constraints, where Y actually also is a binary variable. It just oh, sorry, this is not it. We have x1 and x2 that are binary variables, and they are deciding whether we have gone to the first store or to the second one. If we did go to the first store, then x1 must be equal to 1 and x2 must be equal to 0, and the other way around if we went to the second store. How do we, like, what do we see in these constraints? Well, if we did go to the first store, then this part here must be equal to 0, and therefore we will have an inequality A1y less than or equal than B, which needs to be enforced, while the second inequality will be some number less than or equal than some number that is bigger than everything that could ever happen in this problem, because this thing here is 1, which implies that the second constraint just doesn't matter. It will become an obvious tautology. So we don't need to care to worry about that. So this is in case x1 is equal to 1. And in case the x1 is equal to 0 and x2 is equal to 1, the two inequalities switch their roles, and the second becomes important and the first one becomes obvious. So basically, this is how you would impose a logical constraints, specifically a disjunctional logical constraint in this case. And please do see the file on logical conditions on big courses. I have uploaded it for more examples and explanations. Are there any specific questions regarding modeling of this disjunction condition?
Yeah, one quick question. What is the difference between Y1 and Y2 on this previous graph?
Yeah, so basically, Y1 would be the vector of Y's if we have went to the first store, and Y2 would be the vector of Y's if we have decided to go to the second store. You don't need to like, first of all, there might be different varieties of goods that belong to the different stores, but mainly they are introduced as different variables just to in order to have the nice picture here, so that you have two different variables. You can draw them like one versus the other.
Okay.
Okay. So let us formalize the notion of formulation and how they are being introduced, and what is actually happening when we are introducing formulations, and how to compare them. So first of all, okay, so in order to do that, we would need to introduce a few formal definitions. First of all, a polyhedron is a subset of Rn that is described by a finite number of linear constraints. So we have seen this a lot so far. A here is a matrix, X here is a vector, B here is a vector, and a polyhedron P is a set that is described is the set of Rn where the system of inequalities hold. A polyhedron is a formulation for a set X that is subset of like real, like the integers to the power of n. So the integral vectors times the space of real vectors. If and only if the set X can be obtained as an intersection between the polyhedron P and this set of integral, like some mixed integral vectors, we would call them. So if you have a subset of mixed integral vectors, the projection of Q onto the first n components. Oh, sorry. This is for any set. It doesn't have to be mixed integral, obviously, but the projection of Q onto its first n components is going to be denoted as projection of Q onto the n components, which is the set of vectors in Rn, for which there is a vector in Rp such that xw is a vector in Q. Let me show you a picture of it. So let's say that we have a three-dimensional polyhedron here, and we are trying to. So this is our like first and second variables, and we have the third variable, and we would like to make a projection. So this thing is we would like to make a projection onto the first two variables of this polyhedron Q, where this is the polyhedron Q. The projection is going to take this form, which basically means that this point here does belong to the projection if there is somewhere a point where like, let's say, as like this line is being intersected with Q. For example, here, all of this, let's say all of this points here would be such points. So we just it's just the notion of orthogonal projection onto like that is parallel to one of the to some of the axes in the problem. This is what projection is, and we are saying that a formulation is an extended formulation for a set X. If so an extended formulation is a polytope that belongs to a mixed integers, a set of mixed integral vectors, such that that the projection onto the first several, like let's say n plus p dimensions of it is a formulation for X. So Q itself does not need to lie in the same space X lies in. It just needs to be possible to project it onto the same space, and when it's being projected, after it has been projected, it should become a formulation of X in order to be called an extended formulation of X. Any questions regarding this definition of the formulation and extended formulation?
Yeah, can you define what a polytope is?
Sure. So polytope and polyhedron are essentially the same things. Yeah. So so it also a polytope would be like a finite polyhedron. So it also is defined with a set of linear inequalities.
Okay, thank you.
Any other questions? Okay. So yeah, this is the concept of projection. So not all of the formulations are born equal. And let's consider two formulations, P1 and P2, of an integral problem. Let's say that in total we are interested in the following. Like in the end of the day, these are our feasible points. In both cases, no matter which formulation, P1 or P2 you pick, P1 intersected with the Z2 space is the same set X as the set X that is P2 intersected with Z2. Do you agree with me? So all of these points belong to like are defined by both formulations, and therefore these formulations are called equivalent. We would need to understand which equivalent formulations are better or worse. But before that, let's introduce some more definitions and notations. We are saying that a linear combination of vectors x1 through xt is a vector y that is obtained as a summation of xi's with some scalar weights lambda i's. So this is basically a definition from linear algebra. Now, a combination is conic if all of this the coefficients lambda are greater than 0. A combination is affine if the sum of all of these lambdas, okay, so it should be greater than or equal than 0. A combination is affine if the sum of this lambda is equal to 1. And a combination is convex if it's both conic and affine, meaning that all of these lambda t's are being greater than or equal than 0, and they all sum up to 1. Yeah, are there any questions regarding what a convex combination is? Because this is a kind of a key concept. Okay, so we are defining a hull, conic, affine, or convex of a set X to be a set of all possible combinations, conic, affine, or convex, all finite subsets of X. The convex hull is denoted with conv of X. We are saying that a set X is convex if its convex hull is equal to itself. There are other definitions of it, but this is one that you could use. And the main property of it is that obviously the convex hull of a convex hull of X is the same thing as just the convex hull of X. So basically, if you are having a convex set, if you're trying to convexify it, it doesn't get any more convex than it is already. For an illustration, you can view for yourself the following picture. A convex set is a set such that for any pair of points x, y, every line segment between these 2 points actually also belongs to the set. A non-convex set, for a non-convex set, there is an example of 2 points x and y for which some part of the line segment between them lies beyond the set itself. This is a picture to keep in mind. Any questions regarding the convexity, convex sets, and convex combinations? Have you seen convex sets before and non-convex sets?
Could you explain a little bit more about the convex, like the different kinds of hulls and how that proves that a set is convex or not?
Sure. So once again, this is the definition, and this does not prove much. It's just defines things, right? But I can definitely speak more about different types of hulls. For example, let's say that we have a set that is that consists of a finite number of elements. Where do I write it down, by the way? Okay, let me try to write it here, but okay. Actually, you know what? Let me open special. Okay, let's write right here. Okay, so let's consider let's consider a couple of vectors, v1 and v2, and so they are if you are considering their convex hull, the convex hull of the set of two vectors of 2 points, you would need to consider this line segment between them. Why? Simply because it is a set of all possible combinations. In this case, it's only so this set only consists of two points. So you can only combine these 2 points. So it's the set of all possible combinations. In this case, convex combinations of all finite subsets of X. So this all finite subsets in our case is going to be trivial just for the simplicity of the example, but it won't. I hope I will be able to illustrate the idea. So every vector y that is lambda 1 v1 plus lambda 2 v2, where lambda 1 plus lambda 2 is equal to 1, and lambda 1 and lambda 2 are greater than or equal than 0, should belong, every y of this form should belong to a convex hull of our set that contains 2. So our set X here is just two vectors, v1 comma v2.
Should it be greater than 0, not greater than or equal to?
So it should be greater than or equal to here, here this thing is actually let me correct it. So this should be greater than or equal to 0 because so basically if it was just greater to 0, then v1 and v2 themselves would not be part of convex hull of X, right? So right now, if you substitute lambda 1 equal to 0, lambda 2 equal to 1, you will get v2. If you substitute lambda 1 equal to 1 and lambda 2 equal to 0, you will get v1. So X itself does belong to the convex hull of X. Now, if we pick any point between them, let's say that our v1 had coordinates x1, comma z1, and v2 had the coordinates x2, comma z2. Then our vectors y would be of the form lambda would have coordinates lambda 1 x1 plus lambda 2 x2, lambda 1 z1 plus lambda 2 z2. This basically means that any of the okay, so basically any combination. So if you basically if you introduce your let's say this is our grid, right? This is gonna be X and this is gonna be Z. Then if you just consider this the dimension here, the dimension X, the X coordinate of vector Y is gonna be is gonna split this segment on X as lambda 1, lambda 2, and the same here, and the same thing is going to be happening here. So this segment on the Z dimension is going to be split into is going to be split by the coordinate of Y into lambda 1, lambda 2. So essentially, what we're having here is that the coordinate of Y is going to be such that Y is going to belong to the linear segment between V1 and V2. So this could be an exercise. If you drop this condition of lambda 1, lambda 2 being greater than or equal than 0, then instead of just the linear segment between these 2 points, you would get all of the points on the line. So this is called the affine hull. And if you come back to the constraint lambda 1, lambda 2 greater than or equal than 0, and instead drop the linearity, the affinity constraint lambda 1 plus lambda 2 is equal to 1, then you will get a conic combination, which is any of this it's going to contain any of the points in this cone, in the entire cone that is defined by v1, v2. So this is going to be all of these points. This is going to be this is going to be the conic hull, and this is going to be the affine hull, and the linear segment between the 2 points is going to be the convex hull. Does that answer your question at all?
Yeah, I think it helps. I'll definitely look over it. Thank you.
Sure. If you need any further explanation, please do let me know, because we do have some time for that. Any other questions? Okay, so beyond convex sets, we also have convex functions. A function f is told to be convex over X if for all x1 and x2, for any x1 and x2 in the domain of the function x of the function f, and for a lambda in 0, 1, it holds that lambda f1 f of x1 plus 1 minus lambda f of x2 is greater than or equal than f of lambda x1 plus 1 minus lambda x2. How can we imagine it for ourselves? Well, here is the graph of it. You have a function f. You have two arbitrary points x1 and x2, and you are considering. So on the left hand side there is this point lambda x1 plus 1 minus lambda x2. This point belongs to x, to the domain of the function, and in this case this point. It is first of all, we need to say that this is a conic. Oh, sorry, this is a convex combination of these 2 points x1 and x2, because lambda. So this is lambda 1 and this is lambda 2 here, and their sum is obviously equal to 1, and both of them are greater than or equal than 0, just because lambda is between 0 and 1. So this new point, let's call it y. This new point y must belong to the line segment between x1 and x2. So it is situated somewhere between these 2 points x1 and x2. Moreover, we have also two values of the function. One is f of x1, and another is the f of x2. And we have a convex formulation. Oh, sorry, a convex combination of these 2 points, f of x1 and f of x2 too, which is written right here. This is the first. This is f of x1. This is f of x2, and we are multiplying them by lambda 1 and lambda 2, which also gives us a convex combination of f of x of this, basically of these 2 points that belong to R now. So we have two convex combinations here, and what our definition is saying is that the function f is told to be convex if the value of the function at the point y, which is the convex combination of x1 and x2 of 2 points in the domain, the value of the function must be lower than the value of the linear function that joins these two points, or in other words, the convex combination of the values of this function in the 2 points x1 and x2. So this is the value. This is the convex combination of 2 values, and this is the value at the in the convex combination, and the value of the convex combination must be smaller than the value than the convex combination of 2 values. If this condition holds, we are saying that a function f is convex. Another way to quantify it or to define it is to say that the upper level set, so if you have a convex function, then it's the set of points that lie above the graph of the function is convex. So this set above must be a convex set if we are talking about a convex function. So there is a relationship between the convexity of the sets that we have defined previously and the convexity of the function. We are saying that a function is concave over a set x if the negation of f is convex. So basically, we are saying that a function of this type is convex if after multiplication by -1, it becomes a convex function. So it becomes to look like something like this. a function is both convex and concave if and only if it is linear. So if we have a function that looks like this and it looks like this at the same time, then it must be linear. It must be a line. Any questions about the notions of convexity and concavity for functions? No questions for now? Okay. So now we are coming closer to our understanding of how a formulation would needs to look like. We have a proposition that is saying that if f is a convex function, then maximization of this function over any set, essentially any set, is the same as maximization of this function over the convex hull of this set. For example, if you have a set like that has a weird shape, a discrete set, and you have a convex function and you're maximizing it, then maximizing it over the set itself is the same thing as maximizing it over a convex hull of this set, which would look something like this. This is a convex hull of X. One way, one way to visualize it. I should have mentioned this when we were talking about convex hulls. One way to visualize a convex hull is, let's say that your points, the points of your set are the nails on a plane, let's say, and then you take a rope and you put it on this nails, and then you tighten it, and what you're getting is something is a figure that has this boundary, and this boundary, this figure with this boundary is in fact the convex hull of the set that was denoted by the nails. Just as an example. Another proposition that is valuable here is that if X is some mixed integer set that is given to us with a system of linear inequalities, then its convex hull is a polyhedron. So basically, we are saying that if you are having a mixed integer set for which there is a system of linear inequalities, then there is potentially another system of linear inequalities for which you can actually drop this this constraint of having an integrality. You can just remove it and put going into RP here, and replace this system of inequalities with some other system of inequalities. Let's say bx plus cy is less than or equal than d, and this will give you a polyhedron, obviously, and this is going to be the convex hull of this set X. The good news here is that if we have a convex hull of X, if there is if there is a description for us of this convex hull, then we just need to solve a linear problem, because minimizing, if we are given with a task of solving a mixed integer linear program, then we have a minimization objective where we have a linear function, and then we have X belonging to capital X, and if we are looking at this proposition, then we can see that okay, let's put maximum. So we are maximizing a linear function subject to X belonging to mixed integer linear set X. From the first proposition, we can see that, first of all, the function Cx is actually a convex function. Therefore, we can apply the first proposition saying that maximization of the same function over x is the same as maximization of cx over x belonging to the convex hull of the set capital X. And then we have the second proposition, the proposition 1.1, that is saying that this convex hull has a very simple structure in it, saying that this is basically a polyhedron P. So we are saying that this problem now becomes a maximization problem of the linear objective over X belonging to some polyhedron P, which is a linear programming problem. We know that a linear programming problem is a very simple one. So we basically are solving all of the problems simultaneously if we are having this description as a convex hull. Therefore, the ideal formulation for any mixed integer linear program would be the convex hull of all of the points in the set, which in this case is this polyhedron P3. And all of the other sets P1, the formulation P1 and formulation P2 are not as good as this formulation P3, just because the formulation P3 does give us a linear program in the end that is potentially very easy to solve, and the formulations P1 and P2 do not give us a linear formulation, that therefore it is more difficult to solve. Any questions regarding ideal formulations, how we get them, and why they're useful?
Yeah, can you explain again why P3 is the whole?
Yeah, so if we are having this nails, as I said before, these are the so you do understand that this points that I crossed out are the feasible points for all of the formulations, for the formulation P1, P2, and P3. Do you agree with me?
Yeah. So
Okay.
is it like the smallest possible area that covers all of them?
Essentially, yes. So
Okay.
a convex hull is the smallest possible convex set that covers all of the points in the set. This is another definition of a convex hull. I had no idea that this would be much easier for you. So it is a definition as well that got like, okay, so convex hull of X is the smallest like by inclusion, the smallest set, a convex set V such that X is actually a subset of V. This is another definition that you can use, and P3 is obviously this set. Any other questions here? This is a very good question, by the way. Okay, so let's go on. Now that we know what is the ideal formulation, what is the formulation that we absolutely love to have, let's see how we can compare between formulations. We are saying that the convex hull was the smallest set, and therefore the smaller the set, the smaller is the formulation, the better it should be, like intuitively. So formally, we are saying that a formulation P1, if we are having two formulations P1 and P2 for the same set X, we say that P1 is better than P2 if P1 is smaller than P2. And if we are having extended formulation Q1 and Q2, then the correspondence between them is determined by the correspondence between their projections. So if you have two some weird two weird extended formulations in the higher dimensional space, and you are trying to project them onto the same space, you're projecting one, you're projecting the other. Okay, sorry. This should be something like this. We are saying that if the projection of Q1 here, the projection of Q1 is smaller than the projection of Q2, which is here, of Q2, then we are saying that Q1 is better than Q2 for the same reason as for the original formulations. Any questions on how we compare between formulations? Okay. If there are no questions, let me switch to an example. The example is the uncapacitated lot sizing problem. We aim at designing a production plan for a single product over n period of time. We are given first. We are given the fixed cost of producing in period t. So we are having several periods of time. This is going to be our time. Okay, this is bad. Let's say that our time is capital T, and we are having several periods from 1 to capital T. And we are having a fixed for each moment of time, a period of time T. We are having a fixed cost of production ft, which means that if we decided to produce in the period T, we would need to pay ft in price, no matter how much we produce. The unit production cost in period T is pt, meaning that if we are producing a single unit of our product in period T, then we incur pt. It will scale as we produce more. A unit storage cost from period T to period T plus 1 is ht, meaning that if we have produced something in period T and we or in period T or sometime before period T, and we have not distributed it to our customers, we did not satisfy some demand with it, and we would like to use it in the future, then the cost of storage a single unit is ht. And that the demand that must be satisfied in period T is given with dt. So at period T, we cannot distribute more than dt, and we actually need to distribute exactly dt. How do we satisfy all of the demand by and minimize the cost of the total cost of production over this finite horizon of time? Well, let us put together the first formulation that comes into mind. So first of all, the variables. Let's denote the yt is the amount produced in period T, the amount of production. St is going to be the amount of stored from T to T plus 1. So this is the amount that we have possibly produced in the past before the period T or in the period T, but we did not use it still yet, and we are trying to carry it to the future, into the future. And xt is going to be a logical constraint, which is going to be equal to 1 if production occurs in time step T, time period T, and is going to be equal to 0 otherwise. The objective is easy to write down. This is the total cost that is being scaled with the amount of production, being scaled with the amount of stored product from T to T plus 1, and also it includes the fixed cost of production in the period T times the identifier if we have produced anything or not. The most interesting part here is the constraints. We assume that we have some number big M, that is, for example, big M might be potentially the sum of all of the demands into the future for T from 1 to capital T. obviously there's no way we are producing more than the total amount of demand. So M is definitely going to be much bigger than anything in this problem. So this big M is going to be here. So assuming that you have available this capital M, the balance of production on period T is going to be written with the following equation: St minus 1 plus YT is going to be equal to DT plus ST. This is the amount of produce that we have carried out from the previous period, the period T minus 1. This is the amount that we have produced so far, and this is amount we have distributed in this current period, and this is the amount that we are going to be storing into the future. So once again, this is the amount of produced during this period of time, this particular period of time. Another constraint in this problem is enforcing the definition of xt. That is saying that well, YT is going to be less than or equal than M times XT, the capital M times XT. When XT is equal to 0, we cannot produce anything because YT must be less than or equal than 0. And when XT is equal to 1, we can produce everything. We are not constrained with everything, with anything. Therefore, it doesn't force the definition of XT. So the complete formulation can be put together like this. Any questions regarding the first formulation of uncapacitated load sizing? No questions for now. So this was the first formulation. My strong belief is that we can do better than that by providing with an extended formulation. The trick here is to introduce additional differentiation in the variables. Suppose that we distinguish between the products that we produce today and the products that we produced in the past. So like basically we are saying that like this products they don't have the expiry date or anything. It's just for the purpose of formulation. We are saying that we're gonna be distinguishing between them, just like if they were like different colors of items. So what are these variables? WIT is going to be the amount of produced in period I to be consumed in period T. Like if we are to compare this WIT with the variables from the previous formulation, we would see that YT would be equal to the summation of WIT overall, like for all I from 1 to T. So this is basically so WIT is something that was produced in period I that we consume now, that we can consume in period T. And if we sum everything that we have produced previously that we can consume now, yeah, I mean our Y before was, I believe it was the amount that we produced. Okay, so we actually this is actually not exactly the thing. So WT is going to be WTT without the summation. I'm sorry about that. And ST is going to be the sum over all I's from 1 to T. And this so this is sum from the past, and this is sum from the future. Like this is sum into the future. This is everything that has been produced in the past for all of the time periods that will come in the future to us. So this is sum over all of such WITs. This is going to be ST in our previous formulation. this does not matter too much for this particular extended formulation. It's just for you to understand what is the relation with what we have had before. Xt will be introduced just as before. It just indicates the production in period t. If there was a production, it is 1. If it wasn't, then it is 0. The objective function remains the same. We can just substitute this definitions of y and s into this new formulation, into this new objective function, and we will get the same, like basically the expression of this objective function through WITs, but it does not make any difference. And actually, for the formal completeness, like if we are to compare this formulation, this extended formulation to the previous formulation, we would still need to keep the variables yt and st. I will say filter y. Okay, so how do we put down the constraints? Now the constraints are taking a slightly simpler form. First of all, the balance in period t is basically the sum of all of the periods of times in the past over all of the periods of times in the past, what we have produced in the past for the current time period must be equal to the amount of goods of production that we're gonna distribute to our customers. So this is the balance equation, and the inequalities that enforce the definition of xt now are slightly more complex, but still it is WIT must be less than or equal than dt times xi. We're definitely not gonna produce more than needed for the day t in the day I, right? If like WIT definitely must be less than or equal than dt. Therefore, basically this dt is instead of our capital M from before. But now it is being controlled by xi just because xi controls the production at time period I, and therefore WIT must be equal to 0 if xi is equal to 0, and WIT can be equal to anything if xi is equal to 1. And this constraint must be held for all I less than or equal than t. Okay, so are there any questions regarding the formulation so far, the extended formulation? This is how you would put it down. YT is not this thing. It's oh, sorry. So this is not the. Let me write it. Let me rewrite this thing completely. So what I meant to say is that YT is equal to sum over all I from T to the capital T, WTI. This is what I meant to write down. So so YT is the sum over all of the time periods in the future of the amount of goods that we are producing now for the period of time in the future. So this is the summation of WTIs for all I's from T to capital T. This is the correct formulation. I would need to correct it on my slides. Any questions about it? Okay, so if there are no questions, let me comment on how do we compare, like why do we actually need this XS and Y S and Y variables in this problem at all. Like we could have just gone without this two things, and we could have formulated this in terms of W's. Well, if we are compared to the previous formulation, we would need to project onto the set of variables. So our set of variables must be strictly comparable with the previous formulation. If in our previous formulation we had x as y as the set of variables, now we're gonna have x as and y and also something else as the extended formulation. Now this our something else is specifically w, and this is what extends our formulation. Now when we are to compare this formulation to the not extended formulation, we would need to project onto the set of x as y, which means that we would need to get rid of w in order to compare them. Let's see what we can get. So if P1 corresponds is the polytope that corresponds to formulation 1, and Q2 is the extended formulation from just recent. Let P2 be the projection of Q2 onto the variables x, y, and s, as discussed before. First of all, it can be shown that P2 describes the convex hull of the domain of the problem. Thus, the extended formulation is the ideal formulation. Before that, we were talking about ideal formulations in case they're not extended, but in this case, the extended formulation, the extended formulations also can be ideal formulations, and often they are the ideal formulations. We just need to project them onto the original space. Second fact that is quite important here is that obviously P2 is a subset of P1. You can just check that the point yt equal to dt, xt equal to dt over m for all t belongs to P1 but not to P2. Therefore, this inclusion is strict, and therefore P2 is not an ideal formulation. Therefore, we can see that we have found two different formulations for the same problem. One of them is weaker than the second one, or the other way around. The second formulation is better than the first one, according to our definition. The second formulation was an extended formulation. So this is an example of an extended formulation, and also the second formulation is the ideal formulation that we could better than anything that we could possibly get. So we could basically use this this second formulation without the integrality constraint and everything, and we would solve the problem exactly. So we also have tried and used a very important trick that is going to be useful for us, and that is actually useful in the real world when you're constructing your formulations, which we use target. It's called the target commodities, which we have used to tighten the formulation. Another way to do that is for the problem of the on the graphs to consider directed arcs instead of edges on the graph. But we will talk about this later. These are the two big kind of techniques that you should try first when you're trying to come up with a tighter formulation for any kind of mixed integer linear programming problems. I believe that this is the main things that I wanted to cover today. Next time we will be talking about relaxations and solving of optimization problems. I want to see if there are any questions. If there are no questions, I think we'll conclude with this for today. Anyone wants an example about convex falls or affine falls?